This problem is a one-dimensional elastic collision for Learning Goal CM3. It's from your textbook, page 253, number 4. What we have here is a collision between two balls. You have a 22-gram ball originally moving at 3.5 meters per second. It hits head-on a 27-gram ball that is stationary. In a head-on elastic collision. Now, if you don't know what an elastic collision is, you're not ready to do this problem. You should go back and read the section, solve a few problems with inelastic collisions. Those are like training wheels, and then you can come back when you know what an elastic collision is and do this one. Okay, let's set this up with a system diagram for before and after the collision. So before the collision, the first ball is going to be moving to the right. V1 equals 3.5 meters per second. Your second ball is stationary. V2 equals 0. After the collision, well, it's a head-on collision, so everything will happen along this line. Once the second ball has been hit, it will move off to the right with some velocity we're going to solve for. The original ball, well, we think it's going to bounce back the other way, so we'll draw it doing that. Its actual direction will come out in the math. And we need to solve for that one too. And we know the mass is 22 grams and 27 grams. To solve this problem, the first thing we need to consider is conservation of momentum. Momentum is always conserved in collisions. That means that if you add up all the momentums before the collision, it will equal the sum of all the momentums of all the particles after the collisions. Momentum is mass times velocity, so we can write out the sum of the momentums before the collision, m1 v1 plus m2 v2, equals m1 v1 prime plus m2 v2 prime. I just want to make a note on vector notation. All the velocities and momentums are vectors. I'm not going to be putting arrows on them, and it's okay if you don't either. It's just we've got so much else going on with subscripts, superscripts, and soon superscripts on superscripts that we don't need arrows on all our vectors as well. It's going to make our solution very, very crowded. All right, now back to solving. V2 is 0. The second ball was originally at rest. So now let's substitute what we do have. All right, I'm going to put in masses in kilograms. It's good habit to always substitute masses in kilograms. You're going to see a couple lines down that we could have put them in grams, and it would make no difference to the solution. But I'm following good habit here. So there's m1 v1, and on the right hand side, m1, here we go, v1 prime And as you see, we have two unknowns here. So if we multiply the left-hand side, and we'll also drop units at this point, now it's going to be nasty working with these small decimal numbers, so what I'd like to do at this point is multiply both sides of this equation by 1,000. So that means we multiply every term by 1,000, so 77 equals 22 v1 prime plus 27 v2 prime. And we're just going to leave it there. We'll be coming back to it. That's equation 1. Next, because this is an elastic collision, not only is momentum conserved, but kinetic energy is conserved. Kinetic energy is not conserved in every collision, only in elastic collisions. So that means if you add up the kinetic energy of both balls before the collision and after the collision, they will be the same. Summation EK equals summation EK prime. All right then, a half M1 V1 squared plus a half M2 V2 squared equals a half M1 V1 prime squared. So there's your superscript on a superscript. A half M2 V2 prime squared. And again, V2 is equal to 0. There I wrote a prime where I meant squared. That's better. And now we'll substitute in values. The halves cancel. There's your left side. And again, we'll multiply by 1,000 to make the numbers look more manageable. And fix that subscript. There we go. And that's equation 2. So you see we have two equations in two unknowns, v1 prime and v2 prime. The first one is linear, the second one is quadratic. To solve this, we'll take the linear one, isolate one of the variables, and substitute in the quadratic. So rearranging equation 1, V2 prime is equal to 77 minus 22 V1 prime over 27. We will take that and substitute it in equation 2. All right, I obviously have something to fix up here. All right. You caught that, right? And that? Okay, back on track. Substituting for V2 prime. Okay, so now I'd like to say that what follows is going to be rather ugly. It's going to be quadratic with some pretty nasty numbers in it. But if you can solve this problem up to this line where you've got your two equations right for conservation of momentum and conservation of energy, you have isolated a variable, substituted in, this gets you a level 3. You've done all the physics right and you understand how the solution happens. But if you want the level 4, you're going to have to solve this thing. And so that's what the rest of the video is going to be, solving. Yeah, it's a thing of beauty. I'm going to switch the left and right side as I do this. So starting with the 22 V1 prime squared. Okay, now we've got this squared rational term. It means the top is going to be squared and the bottom also has to be squared. The top is a binomial, so you're going to square it using FOIL. And when you do that, you get 5929 minus 3388 V1 prime plus 484 V1 prime squared. So that's the top, and the bottom is going to be, I'm not going to multiply it out, I'm just going to write 27 squared. All right, and that equals the 269.5. All right, so the 27 here cancels with one of the 27s down there, leaving 27. So you've still got a nasty fraction. We're going to solve that problem by multiplying every term by 27. So 27 times the first one is 594 V1 prime squared. For this whole term, multiplying by 27 just cancels out the denominator. So we keep what's on top. And on the right hand side, times 27, 72, 76. 0.5. Yeah, this is a quadratic, so we'll gather our like terms. We've got two v1 prime squared terms. So add those. You have 1078 v1 prime squared minus 3388 v1 prime, and you take your other two terms, you end up with negative 1347.5. Okay, so we've got everything lined up to go into the quadratic formula. So v1 prime is equal to negative b, so 3388 plus or minus the square root of, this can be a big one, b squared minus 4a c all over 2a. All right, so if you work out what's under the big square root sign and then take the square root of it, you have 4158. The bottom here is 2156. So there's two solutions to this. If you take the plus here, you have V1 is 3.5 meters per second. If you take the minus, V1 prime is negative 0.357 meters per second. All right, so now only one of those can be correct. Let's go back to the very top. Our original situation, the first ball was moving to the right at 3.5 meters per second. We know it has to slow down because it's given some of its kinetic energy to the second ball. So that first solution cannot be right. The negative solution, where it's bounced back the other way, going slower, is clearly the correct one. So we will reject that and take the second one. And now we can solve for V2 prime. We need to substitute back into here. All right. So substituting back into that start equation, V2 prime, I'm just writing it again, 77 minus 22 V1 prime over 27. So 77 minus 22, negative 0.357 meters per second divided by 27 is 3.1 meters per second. So therefore, our V1 for the first ball, the 22-gram ball, it will bounce back at 0.36 meters per second. I've taken it down to two significant digits. the 27-gram ball moves forward at 3.1 meters per second. Okay, to recap then, you need to start with your system diagram. What's going on before and after with all your givens listed. In the after, sometimes you have to guess at the direction, but like I said before, it'll all come out in the math. We solved for v1 prime being negative, meaning we were right, it went back the other way. In every collision, momentum is conserved. So that's the first thing you do. This collision is a perfectly elastic collision, so kinetic energy is also conserved. You end up with two equations in two unknowns, so you need to isolate one of the variables in the linear equation, substitute into the quadratic one, and like I said before, if you get to that point, you've done a good job and you're at level 3. The rest of it is all math. Sometimes it's nasty like this, but in the end you will solve for the velocities of both balls. So that's it. Good luck with your own.